This is an introduction to gases and the relationship between different variables of gases. So a couple things to remember. We use the kinetic molecular theory, KMT, which assumes a couple of things. One, that there are no intermolecular forces of attraction, and this is related by the statement that all collisions are completely elastic. So remember from physics class that if all collisions are completely elastic, it means that there is no stickage or squishage, and energy is completely conserved. Also, that temperature is a measure of the average kinetic energy. And the gases act as point particles, which means that the volume of the particles themselves is much, much less than the volume container. As a result, we can say that all the gases basically behave the same. And that pressure is a measure or is proportional to the number of collisions over a given area or volume. So if I increase the number of collisions, then the pressure will increase. So the factors that affect the pressure of a gas are going to be the volume of the container, the temperature of the gas, and the number of particles that I have in that container. And it's going to be a container. Even if we're talking about atmospheric pressure, we can talk about the container of our atmosphere. So our first relationship is going to be volume, pressure and volume. And when I'm looking at two variables, that means that two of my other variables remain constant. So N, which is standing in for number of particles, moles, and the temperature are going to remain constant. So an example is bubble wrap. So if I have bubble wrap, and we all love bubble wrap, if I decrease the volume, then the pressure increases. Or if I pull it apart, the pressure decreases. So it's an inverse relationship. Mathematically speaking, we express inverse relationships as the two variables multiply together equaling a constant. And the graph of this inverse relationship is a hard curve. So the reason why this happens, kinetic molecular theory wise, is that if I increase the room that the gas has to move around in, and remember that gases always take the entire volume of the container given to them, the number of collisions against the side of the container go down. And so imagine little toddlers running around in a room. If they're in a small bouncy castle, they're hitting the sides of the bouncy castle all the time. Pressure against the walls is like going like this. If I expand the size that's given to them, they're going to hit the sides of the container less frequently, and so the pressure is going to go down. Or if I decrease the volume with bubble wrap, then the pressure will increase to the point where it bursts through the bubble. So we don't like these graphs. So if I have this, PV equals a constant, I can make it into P and divide both sides by V is equal to a constant times 1 over V, right? So that would be constant over V, or I can just simply say constant times 1 over V. And that's in a y equals mx format. Y is the P, the constant is the slope of my line, and the 1 over V is my x value. So the point of this is that I can create a linear graph off of a nonlinear graph if I have this relationship simply by graphing P over 1 over V. And the slope of that will be a constant. We like y equals mx plus v. Pressure and temperature. So it's a direct relationship. As I increase the temperature, the kinetic energy of the molecules increases because we define temperature as a measure of the average kinetic energy. Now remember that kinetic energy is 1/2 mv squared. The mass is not changing, which means that the velocity has to increase. So if the particles are moving around a lot faster, the number of collisions will also become higher, so the pressure increases. So as the temperature increases, my pressure increases. It's a direct relationship. So I can express that either as P over T is equal to a constant, or T over P is equal to a constant. And these are not the same, it's just a constant of the thing. So an example are exploding tires. If I'm driving on the highway and I have tires that are very thin, the inside of my tires gets very hot because of friction. It can increase the pressure of my tires, and that's why they start to blow out. Right? So blowouts only occur on highways because that's the only time in which you're having a speed that's high enough to create high enough friction, which will generate high enough temperature, which will increase the number of collisions to the point where it's too much pressure for the tire to take. You're not going to have tire blowouts on a very bumpy dirt road because you're just not going to be going fast enough. Now the thing is, when I plot this as a function of pressure over degrees Celsius, there's a y-intercept. We don't like that. We love graphs that have no y-intercept, so I can just say that y equals mx. So I transform that, I shift this over so that my pressure and temperature graph are now not just a direct relationship, but it has its intercept at the origin. In order to do that, I have to change my temperature units to Kelvin. There's a nice thing about this. You want that to happen because if I had P over T is equal to a constant and I was using a negative degrees Celsius, it might imply that my pressure is negative. So I've never seen a negative pressure before. I don't know what that looks like. Or it would imply if I have degrees Celsius here as 0 that there's no pressure. We know that's not the case because there have been many times in which the temperature has been less than 0 degrees Celsius in New England, and it's not like the gas around us ceases to move. This also implies that at a 0 temperature in Kelvin, I have no gas pressure, and that can only occur if I have no collisions, which can only occur if my velocity is 0. So absolute zero is a scientific concept in which all motion ceases to exist, including electrons around protons and things like that. Fairly catastrophic. So we actually haven't achieved absolute zero, we've gotten very close. And in this case, yes, if all motion ceases to exist, because my temperature is at 0, then I would expect no collisions and therefore no pressure. Volume and number of particles, right? So as number of particles, moles, goes down, if pressure and temperature are constant, the volume will go down. So an example is a leaky balloon. If I'm losing gas from my balloon, it will shrink in volume. It's a direct relationship, and it goes through the origin. There is no y-intercept. And that makes sense because if there's no gas in my balloon, there won't be a volume of gas. So an expression of that is V over N is equal to a constant, or N over V is equal to another constant. Now all of these can be derived from the ideal gas law, right? So, or they form the ideal gas law. So if I'm looking at the three equations, PV is equal to a constant, P over T is equal to another constant, that's why it's in a different color, and V over N is equal to a constant. And this is assuming that you're in Kelvin, right? So I can rearrange this and say P is equal to a constant times T, the green constant, and V is equal to a red constant times N. So then by the property of substitution, PV is equal to PV. I can say PV is equal to this constant T times this constant times T. Well, a constant times a constant is a constant. And that constant becomes R, what we call the universal gas constant. So I can rearrange this and say T and N are still my variables. PV is equal to nRT. All other gas relationships can be derived from PV equals nRT. So this, in fact, is the only gas equation that you need to know when you're looking at relationships between pressure, volume, number of particles, and or temperature. And the universal gas constant is a value. It depends on the units of P. Because there are many different units of P, that value of R will depend on the units of P. So just be careful. Most of the time we'll be working with atmospheres, but just be careful, especially in your gas lab.